We're going to start by talking about something. I'm going to start by talking about the number pi for a minute, okay? This is an irrational number. If you write it with a decimal, 3.14159.26535, right? And continues on and on. It's an irrational number, so there's no pattern in that, and it's not going to terminate. So what do we mean when we're writing this number pi with decimals? When we write in decimal notation, you can think of this as being a sum. 3 plus my number in the 10 spot is 1 over 10. The number in the 100 spot is 4 over 10 squared. 1 over 10 cubed. 5 over 10 to the 4th. 9 over 10 to the 5th. Okay? So I write this plus dot dot dot. So what does that mean? Well, as I add more and more of these fractions, I'm getting closer and closer to the actual number pi. Okay? So really, what is this? This is a sum of an infinite number of terms, right? I have an infinite number of terms here. So we can connect this idea with our talk of sequences in the following way. If we have a sequence, a sub n, and we take this sequence and we add up these terms, then what we're looking at is something that looks like a1 plus a2 plus a3. The general term is a sub n, which looks just like this expression I had for pi. It's an infinite list of numbers that I'm adding together. And so this is what we call, is called an infinite, or sometimes they leave the infinite off, infinite series. And the way we're going to denote this is with a summation symbol, a sigma. Have you seen that before? Yeah. Sigma, capital sigma, that's just sum, right? And sometimes if it's understood what the bounds are, sometimes it'll just say sum a sub n without the n equals 1 to infinity part. So, okay, I know what a series is now. I take a sequence and I add up all the numbers in the sequence. But let's stop for a second and ask ourselves the following question. Does it make sense to talk about the sum of infinitely many terms?
No, it makes no sense at all.
It seems like it doesn't, right? But in the case of pi, it was okay, right? I had an infinite number of things added together, and that's just pi. So it seems reasonable for the example we started with, where we were talking about pi. So let's look at some examples just to see, okay? So let's start with, let's say the series I'm looking at, 1 plus 2 plus 3 plus 4 plus 5. So in general, I'm adding the number n. And I want to talk about the sum of this infinite list of numbers in my sequence n. Okay? Well, let's just start adding terms. Okay? So let's start the first time I can count a number, 1, and then I'm going to take 1 plus 2, that's 3, right? 1 plus 2 plus 3, 6. 1 plus 2 plus 3 plus 4 is 10. 1 plus 2 plus 3 plus 4 plus 5 is 15. And then you'll get 21. So it looks like if I just start adding up these numbers, right? And looking at the sums that I'm getting, they look like they just keep growing, right? Well, there's actually a really nice formula for if I add up the first n integers, it's n plus 1 over 2. Okay. Have you seen that formula before? If not, it's a very famous one. And if you Google the sum of the first n integers, you'll see this formula on the internet, okay? So what happens as n gets larger? I want to know what happens to my sum over here on the right. What happens as n gets larger? Well, let's look at what happens over on the formula side. What happens as n gets larger to the numerator? It gets larger, and I'm dividing by a constant number, so it looks like this sum here becomes very large as n increases. Okay? So in this example, it wouldn't make sense to talk about the sum, because when I start adding up numbers, the numbers grow, the sum number becomes too big, too fast. Okay? So let's look at another one. Let's say I want to take the numbers 1/2, 1/4, 1/8, 1/16, 1/32. So in general, my general term is 1 over 2 to the n. And I want to see if it makes sense here for me to talk about the sum. So I'm just going to repeat what we did on the last example. Let's just start by adding the numbers together. So my first one, I get 1/2. 1/2 plus 1/4. What's that equal to? 3/4. 1/2 plus 1/4 plus 1/8. 7/8. Great. Okay, this one's a little bit harder for us to add. But you're gonna keep going. 1/2, 1/4, 1/8, 1 over 16. 15 over 16. If you include another number, 1 over 32, you're going to get 31 over 32 for the next one. Okay?
So he'll never approach 1, like that's the upper we talked about balance.
Yeah, right? These numbers are not growing too fast. This isn't like the last example where the numbers were getting really, really large. It looks like my numbers are always going to be less than 1, right? And it looks like it gets closer and closer to 1. So if I take in general, if I'm adding up these numbers up to 1 over 2 to the n, the formula for these sums here, it's going to be 1 minus 1 over 2 to the n. Because the numerator is 1 less than the denominator. Okay? And what happens as n gets large to this right-hand side here? This part approaches, this little part here approaches 0, so overall it's going to approach 1, right? So this, in this case, it makes sense to talk about the sum. And you would write that the sum from n equals 1 to infinity of 1 over 2 to the n is 1. That's because you're looking at this limit of this guy here, and you got 1 for that limit. Okay? Any questions so far? Yeah.
Where did the 1 minus?
Where it came from was, I noticed in all of my fractions, the denominator is 2 to a power, right? 1/2, 3/4, 7/8, 15 over 16. So the denominator is 2 to the n. And the numerators are always 1 less than the denominator. So in the end, where it came from is I said this was 2 to the n minus 1 over 2 to the n. But then I can simplify that and just divide and get 1 minus 1 over 2 to the n. Okay? Other questions?